On to the final part of this chapter, logarithms and nonlinear data. This is all about taking a graph that you would have a logarithmic graph or exponential graph and convert it into a linear graph so that you can see trends in the data. You'll have seen this recently in some of the COVID-19 graphs where on the y-axis they've been using a logarithmic scale so that you can compare different countries more easily on one graph and also not to scare everyone too much. It's got two cases to consider. Case 1 is where y equals a x to the n. So an exponential graph where you've got x and then the power is n. So first thing we're going to do is take log to the base 10 of both sides. Now from this point forward, if you're ever doing log to the base 10, you can just refer to it as log. And that is represented on older calculators with its own button. So on here, log is log to the base 10, it's the same thing. So first thing I'm going to do is take log to both sides, or log to base 10. I'm then going to split this up using the multiplication rule. I'm then going to bring this forward using the power rule. I am then going to swap these two over. The reason being is because now it looks like y equals mx. It's the general equation of a straight line. So the vertical axis is going to represent it with log y, horizontal axis is going to represent it with log x, the gradient is going to be n, the power, and the intercept on the vertical axis is going to be log a. Okay, so in terms of a graph, we would have log x on the horizontal axis, log y on the vertical axis, a straight line graph where the intercept is log a, and the gradient would be n, the power in the original exponential graph. So if we now look at example 19, excluding London, we've got the next 5 cities in terms of their population. I'm not sure how accurate this is, but here we go. And you can see if we were to plot this as rank on the x-axis, population on the y-axis, you'd get some kind of exponential graph. So what we're going to try to do instead is represent it with a linear graph. So the model suggested is p equals a r to the n. If you've got an older textbook, that was wrong in the textbook, you got that the wrong way around. We'd need p equals a r to the n. So log to both sides, split that, bring the n in front, swap these two over, compare to y equals mx plus c. So we would have log r on the x-axis, log p on the y-axis, gradient would be the power, intercept would be log a. So what I need to work out firstly is log of all these values and log of all these values. So log 2 is 0.30, 0.48, log 5, 0.70, 0.78. And then doing the populations, log a million, 6, log 730,000, 5.86, log 620,000, 5.79, log 530,000, 5.72, log 480,000. .68. So let's now plot these on a graph. So 0.3 is 6, 0.48 is 5.86, 0.6 is 5.79, 0.7, 5.72, 0.78, 5.68. As you can see, that does form a more linear pattern. If we draw a line of best fit, we can see that it goes through the y-axis at 6.2. So 6.2 equals log A. Intercept on y-axis, or in this case log p-axis, is log A. And the gradient, I'll just measure that. So we're going from 6.2 to 5.5. It's 0.7. And across 1. So the gradient would be minus 0.7 over 1, which is obviously minus 0.7. So in the original model, because we were asked to find A and N, log A is 6.2, but remember this is log to the base 10, which becomes 10 to the power of on the other side. So 10 to the power of 6.2 is 1, 5, 8, 4, 8, 9, 3, or to 2 sig figs. $1,600,000, and the gradient, which would be n, would be minus 0.7. So it'd be P would be represented by 1.6 million times the rank to minus 0.7. Okay, now the second case, case 2, is where we have y equals a, b to the x. So this time the power is x. But similar to before, we're going to do logs to both sides. Split using the multiplication rule. Bring the power in front using the power rule. Flip these, swap these over. And then compare to y equals mx plus c. So this one's slightly more confusing because the horizontal axis is going to be represented by log b and the gradient is going to be represented by x, the power in this case. Vertical axis is going to be log y, and same as before, the intercept on the vertical axis is going to be log a. So on the horizontal axis, we're going to have now, what I'm going to do here instead is write it as log y equals log b x plus log a. So y equals mx plus c, because this is the constant, obviously this is the variable. So the horizontal axis is going to be represented by x, the vertical axis is going to be represented by log y, the gradient is going to be log b, and the intercept on the vertical axis is going to be log a. So the gradient log b over 1. Okay, on to the final example then. This is to do with the population of bacteria over T hours. We've got T and log P, 2, and then you can see it's getting bigger, the bacteria is growing. So it says the suggested model is P equals A, B to the T. So again, if we now represent that in a linear model, logs to both sides, split using multiplication rule, bring the T in front and the power rule, swap these over, swap these over, and then compare to y equals mx plus c. So the intercept log A, vertical axis, horizontal axis rather is T, gradient log B, and the vertical axis log P. Now we're told actually in the graph it went through the point 0, 2 and it had a gradient of 0.6. So using our model then we can say that log P must be equal to 0.6t plus 2 because log A is 2 and the gradient was 0.6. Now, trying to get that back into this form, we can, remember this is log to the base 10, you can do 10 to the power of to this side, bring all this across, so P equals 10 to the power of 0.6t plus 2. We could split this using just simple power rule. And then if we just swap these over, just to match the model. So I is going to be 100, B is going to be 10 to the power of 0.6, So to represent this graph in this model, I would have to be 100, B would have to be 3.98. So that would be the original amount of bacteria, initial size of the bacteria population. Okay, that's all the examples on this chapter done. You can now have a go at exercise 14H plus the mixed exercise.